Welcome back to campus, alumni and children of alumni and family of alumni. We're here in the bowels of the physics building, the basement, in my laboratory, a place where few people have gone before. My name is Sam Sampere, and for Orange Central this year, we're doing some virtual science experiments, some things you can do at home, create for yourself, go out and explore on your own. I have a container with some water in it. I have Dawn dishwashing liquid. Dawn works really good. So if you can get Dawn works really good. I have a 2-liter empty soda bottle that's been cleaned. A torch. You don't need a torch. You can use a stove. You can use a match, something. All I want the torch for is to heat a nail to poke a hole in the bottle. So let's do that. We'll turn this on. We're going to heat up the tip of my nail. And all I want to do with this nail is poke a hole down here in the bottle. That's all I want to do. And I'm not going to, oh, I did it, darn it. I poked the nail all the way through, which I didn't want to do, but we'll live with it for now. Let's cool the nail off. Okay, the nail's cool. That's not why I need the water. In here I have 6 parts water. Now I'm going to add 1 part of the Dawn dish soap. So if you have 6 cups of water, you're going to add 1 cup of dish soap. Let's stir this up. What I've made here is a really good solution to make big soap bubbles. That's what's in here. And if you want to make even better soap bubbles, you would add some glycerin or corn syrup. Okay, soap solution, 2-liter soda bottle. I'm going to pour some of that soap solution in. I don't need a lot. I'm going to plug this up. Why did I want the nail? Because I want to plug up the hole that I made so that the soap doesn't leak out, and I made the hole too big, so I'm just going to use my finger right now to plug that hole up. Let's coat the entire inside of this soda bottle with the soap solution. And you'll see why you want that plugged, because I don't want the soap to be dripping out everywhere. Okay, now if I get all the soap down here and then release it, I should have a little soap film left right here. Oh, it just popped. So let's do that again. I'm not even going to cap it. Put my hand here. Let's get that soap film right there. And now, oh, I didn't get this film. There we go. Perfect. So what I did was I started with the soap film right here, and then I gently blew it until it moved down to here. So right here in the center of this bottle is a thin film of soap. And what we're going to do is go out in the sun, and maybe you can even see that in the video right now. You see some colored stripes horizontal across that film. It's going to appear really nice in the sun. And we're just going to watch this soap film change over the course of time as gravity drags the liquid soap film from being uniform to thicker at the bottom and thinner at the top. We're going to see those color bands change. Here's an observation experiment for you. How do you see those color bands changing? What's happening is the film at the bottom is getting thicker compared to the film at the top, which is getting thinner. And then just before this pops, and because this is in a sealed container like this, it's going to stay for quite a long time before it pops. What color is the top of the film before the soap bubble pops? We're done. We've made our experiments. Now it's time to go outside and see what we've created. So right now you should see horizontal bands of color that are going from blue to magenta, or maybe cyan to magenta. And that series just keeps repeating itself. So make your own rainbow bottle, rainbow in a bottle, go outside and have fun playing with soap films. Now we're going to do some science with a penny. So over here I have a penny. I stood that penny up on edge on this piece of wood. Here I have a magnet. It's a really strong magnet. If you don't have one of these neodymium iron boron magnets, a convenient place to get one is from your dead computer. You pull out the hard drive, take the hard drive apart, and you'll find some really strong magnets in there. Take the magnets out. I have some keys. You know this is a strong magnet because it picks these keys right up off the table. The keys are steel. But pennies are made of copper. I'm going to bring this magnet close to the penny, and I'm going to do this slowly. And you'll see that that penny is not affected by the magnet at all. There's no attraction. And let me just remove the magnet away. What I'm going to do next, I'll bring the magnet close to the penny, but instead of pulling the magnet away slowly, I'm going to pull it away fast. I want you to think for a few moments. What will happen to that penny when I pull the magnet away fast? Some possible answers. Nothing happens to the penny. The penny falls that way, the penny falls that way. Or do we not have enough information to tell? Argue with your parents. Argue with your kids. Okay, let's do the experiment and try this. So I'll bring the magnet close to the penny and pull it away quickly. The penny falls towards the magnet. Let's try the reverse experiment. I'm going to do the reverse experiment, bringing the magnet towards the penny quickly, and I promise I will not touch the penny. I didn't touch it. I did that to show you that magnets don't stick to everything that's metal. So this is a penny that's made of mostly zinc with a copper coating, and none of this is magnetic. The penny does not stick to the magnet. This is aluminum. It behaves magnetically the same as the penny. Magnets don't stick to the aluminum. So here I have an aluminum ball. If I were to take this aluminum ball and roll it down the ramp and get ready to catch this over there. Okay, excellent. Perfect. That worked exactly as I thought. Well, in here I have what looks like aluminum, but it's not. It's a magnet made of the same thing as that. Let's watch what happens when we roll this magnetic ball down the aluminum ramp. And remember, magnets don't stick. Okay, you ready to catch this over there? Okay, get ready. 3, 2, 1. Whoa! The magnet doesn't stick to the aluminum, but when it's in motion, there are magnetic fields created that resist the motion of the ball. So what's really cool, if I were to stand this up on end, so there really wasn't any need for anyone across the room to get ready to catch that ball. So this time I'm going to hold the ball up here and let it go. And if you look carefully, you might even see an air gap in between the ball and this aluminum. They won't even be in contact. Remember, if these were attracted because of magnetism, the ball would not fall away from the aluminum track. That is so cool, and you can tell that this is falling much slower than it does without being near the aluminum. So aluminum, no aluminum. So dropping near the aluminum, you could see that air gap, right? Dropping it away from the aluminum, you can also tell that it's a louder sound because it's falling faster compared to here. We're going to use some of these concepts in here to explain our next experiment. We have one final experiment. It ties into the previous two that we did. So if you remember, we had a penny stacked here. I brought a magnet nearby the penny. Well, at that moment, the penny was seeing a really strong magnetic field because of this magnet nearby. And when I pulled it away quickly, the penny saw the magnetic field get small really fast. The penny's a conductor. The penny doesn't want to see changing magnetic fields. So currents were induced in the penny, and when currents are produced, or when I have electric current, I automatically have a magnetic field. And it was just such that the magnetic field created by the currents in the penny were attracted to the magnet as I pulled it away. And hence the penny fell over. Likewise, the second time the penny was sitting here, it saw zero magnetic field. And when I brought the strong magnet nearby quickly, the penny said, oh, I don't want that strong magnetic field near me. So currents were induced, and the magnetic fields created by those currents repelled that change, or opposed that change, and repelled the magnetic field from the strong magnet, and you saw the penny tip over away from the magnet. We're going to exploit that in this next contraption here. Down here in this gray box is a capacitor. I'm going to charge it up to some voltage really high. If you note the sticker on here, lethal. If I were to charge this up, it's going to have the same energy as if I took a 1 kilogram mass, that's a couple of pounds, and brought it a couple of football fields high in the air and dropped it. The energy contained in that mass is going to be the energy contained in this capacitor. No doubt that's lethal. Okay, right now everything's off. There's no charge on the capacitor. It's safe for me to reach inside. So I'm going to open up this shield. I'm going to put a soda can in here. What's the soda can in? Well, it's in a can, or it's in a coil made of 3 turns of this copper wire. So 3 turns of this copper wire is the coil, and that coil is going to get connected to this capacitor after I charge the capacitor. So let's close the door and let's get the capacitor set up for charging. So first I need to plug in the charging circuit. I am going to disconnect ground from the capacitor, and I'm going to lock it in place so I can't accidentally ground it. I'm going to connect my charging rod. And I'm going to open the switch so that I can actually charge the capacitor. So the switch is now open. I'm going to turn the voltage up in small increments. And you'll notice as I do that, that the voltage on this meter starts to increase. When this needle gets all the way over here to 3,000 volts, the voltage on the capacitor is actually 6,000 volts. And if I do the math, I come up with 1,800 joules of energy. So we're just going to slowly ramp this voltage up. After this is charged, we're going to close the switch and let all that charge flow through the coil of copper right there. It's going to be a giant current, huge. It's going to create giant magnetic fields. Right now, the magnetic field inside that soda can is 0. There's no magnetic field. But once that giant current flows in that coil, there's going to be all of a sudden a huge magnetic field. And the soda can is a conductor, remember? It's going to create currents which will make magnetic fields to oppose the magnetic field that's created in that coil of copper wire. So we're almost up to the top. One last little bump up here, and we are at the top of that voltmeter right now. Let me disconnect the charging circuit. Disconnected. I'm going to turn this off. So here we have this harmless looking capacitor here, but keep in mind it has 6,000 volts on it. I'm going to put on some hearing protection. I'm going to open these up right now, and we'll do a countdown. 3, 2, 1. We'll pull out the old coil, close the switch, and see what happens to the soda can. So here's our countdown. 3, 2, 1. Wow, that soda can was ripped in half. Here's half the soda can. Let's see, it's grounded. Yeah, I grounded. It's shorted. It's safe for me to reach in. Here's the other half of the soda can. And this soda can feels quite warm to the touch. Wow, more physics. There is so much physics in this cool experiment. If you have questions or comments, please send an email, cassalumni@syr.edu.